Now my screen is visible, sir.
Yes, we can see your screen.
So the objective of the work, yeah, okay, now I can proceed. So the objective of the work is to design front-end converter, voltage source converter. So which could be either a conventional two-level converter or a multi-level converter, and a back-end converter that is nothing but any DC-DC converter for EV charging station. And then the objective is to do the coordinated control of the front-end converter and the back-end converter. And here we are using the double droop method. So two droops are being used for providing the frequency support, grid frequency support. So these are the objectives of this particular work which I am going to present in today's session. So the basic motivation of all these things arises from the electric vehicle charging systems which are predominantly coming into the grid. So they are going to influence the grid in the near future, and huge voltage source converters power the DC system, that is the multi-terminal DC system, and the various converters are going to be connected to the common DC bus. So in the conventional grid, we have the synchronous generators which have the inertia, and therefore their energy is being stored in the inertial part of the machines, and that could support the support during the frequency crisis. So whenever there is a frequency oscillation, since all the synchronous machines swing together, so together they'll be able to give the required active power support to the grid and thereby stabilize the frequency. But whereas when it comes to the grid, which is predominantly having many number of grid-tied inverters, which are feeding or evacuating the power from the various sources. So both the type of operations like vehicle to grid and grid to vehicle operations, there must be some coordination among the various controllers corresponding to various converters of the grid, so that whenever there is a frequency dip or increase, so the required frequency support would be given. So this is the motivation, and this is the schematic of the diagram. So we have 420 kV AC grid, so 50 hertz frequency, and this we are connecting to two different EV charging bays. The first bay is powered by 420 bar 230 kV transformer, and then of course
Okay, we have an unexpected internet connection issues apparently. Okay, we lost you temporarily. Can you show your screen again?
Are you able to hear me?
Okay, yes, we can hear you. We can see the camera, but we don't see the screen.
Yeah, I'm able to. Okay, my screen share is already going on. So let me proceed with my presentation. So here, the DC bus, we have many number of DC-DC converters connected.
We still do not see your screen, unfortunately. Can you restart screen sharing, maybe?
Yeah. So we have the various DC-DC converters which are powering the battery, and then two different types of droops are being employed over here. So one is VF droop for the VSC converters. So the other droop is named as IV droop. So this IV droop is applicable for the DC-DC converters. And all
sorry,
these droop controllers,
Dr. Anbuselvi, we still cannot see your screen, unfortunately. Maybe to help with possible bandwidth issues, maybe
again,
disable the camera.
Yeah, and, again I do the screen. I'll share the screen again, sir. Now is the screen?
Yeah. Okay. Yes. Now screen is fine.
Visible? Okay. Now the screen is visible.
Yes.
Yeah. I'm sharing my screen.
Yes, but maybe for like to avoid some bandwidth
This
issues, you
system
could disable the
configuration
video.
visible? Yeah,
We
maybe I
can
can
see.
switch off my video.
Yes, thank you. So your screen is visible and we can hear you.
1 second. Yeah. Is my system configuration visible to everyone? Shall I proceed?
Yes, now we are at the objectives slide, so you could continue.
Yeah, this is slide number 4. So slide number 4 shows the system configuration. So here there are two.
Actually, we're on my end, I'm seeing slide number 2.
Oh, still you are seeing slide number 2.
Yes.
1
Maybe
second,
it's a different screen that you're sharing. If you have 2 screens, maybe it's the other one.
Wait. Resume share. New share. Maybe I'll share my window. It's the entire screen. Is this visible? So
All right.
slide number
Yes.
4 is visible?
Yes,
Oh.
now we are at slide number 4. Excellent. Thanks.
Yeah. So now I'm coming to slide number 4 again. Fine.
Yes, now it's clear.
Yes.
Thank you.
Yeah. So here there are two grid-tied inverters, which could act as either inverters or rectifiers. So here voltage source converter 1, this converter is rated 100 MVA and it is connected to 600 kV DC bus. Again, there is another converter which is feeding a huge charging system, electric vehicle charging system. This converter is rated 500 MVA. So there are two converters which are not rated one and the same, and they have to participate in the frequency regulation proportional to the individual ratings, MVA ratings. So this is done by the means of Droop control action. And we have various DC-DC converters. Exactly speaking, in 100 MVA through 100 MVA converter, nearly 16 number of DC-DC converters are connected to the charging system, and to the this particular DC bus, which corresponds to 500 MVA converter, nearly 84 number of DC-DC converters, which could draw 110 ampere current, are connected to the DC bus. So the DC bus voltage is common, 600 volts DC bus, 600 kV, I'm sorry, 600 kV DC bus. And here we have the master controllers, so which give the control commands to various controllers, individual converter controllers. So we go for the independent PQ control, which is a conventional one. So the alignment is D leading Q, and we go for the grid voltage vector orientation. So P is directly proportional to ID and Q is directly proportional to IQ. So the equations governing the outer controller controls are given as below. And the equations corresponding to the inner current references, ID reference and IQ reference, are as given below. So this is the typical controller structure for the grid-tied VSC. It's a very conventional one where we have the VDC regulation and VAC regulation. So when VDC is being tracked, so correspondingly, the required amount of real power is being drawn from the grid. Thereby, the DC bus voltage can be regulated. And we have many number of gain parameters over here pertaining to the outer controller and the inner controller for VDC regulation loop as well as for VAC regulation loop. So, so here nearly 8 number of control there is gain parameters need to be tuned. So the proportional gain and the integral gain corresponding to outer controller, similarly for the inner controller, for VDC loop as well as for VAC loop has to be tuned in a coordinated fashion. So along with that, we have another controller. So which will always track the battery current references to charge the electric vehicle, which is being connected to the DC grid. So the virtual inertia here in the system is nothing but the energy which is being stored in the DC link capacitor. So the half CV squared, the energy which is being stored in the DC link capacitor is freewheeled. So it could be actually freewheeled either as a real power or as a reactive power. But since our objective is to give the grid frequency support, so here corresponding to the dip in the frequency, the real power support is being given. Suppose if there is an increase in the frequency, more amount of real power is being drawn from the grid in order to regulate the frequency. So the virtual inertia which is present in the system is nothing but the energy stored in the DC link of the system. Okay. So in this work we are considering coordinated double droop control strategy. That is, initially when there is a dip in the frequency, the first and the foremost one which will give it the support is nothing but the grid tied VSC itself. So proportional to the dip in the frequency, the voltage reference, DC bus voltage reference will be modulated so that this participates, that is a VSC will participate in the grid frequency regulation. Subsequently, after some 1 or 2 cycles, IV droop also is being invoked. This IV droop pertains to the battery charging ports. So whenever there is a dip in the DC bus voltage sensed, correspondingly, the I battery references also are modulated. So this is IV droop control strategy, which comes subsequently following VF droop control. So the droop coefficients K1 and K2 are given as shown. So this droop settings are proportional to the MVA rating or the KVA rating of the converters. So K1, that is droop setting of converter 1, VSC 1, is nothing but delta VDC1 over delta F, and K2 is delta VDC2 over delta F. And the equation for the droop control is given as, so the new reference, VDC reference, is nothing but equal to the old reference plus droop times the frequency deviation, that is F measured minus F reference. And the droop control structure of VSC is as shown in this figure. So VF droop control structure is basically this droop control modulates the reference. So we have a delta V signal which will arise, okay, only whenever there is a dip in the frequency. If there is no dip in the frequency, this delta V would be 0. So whenever there is an increase or decrease in the frequency, delta V becomes non-zero. So either it would be positive or it would be negative. So it modulates the VDC reference. Same in the voltage, correspondingly, VDC reference also would be reduced, and thereby the DC bus voltage, which is 600 kV, will not be maintained exactly at 600 kV, very small magnitude. So this is your V by, that is VF droop schematic. And subsequently what will happen is, so if this frequency dip is going to be prevailing and if the DC bus voltage reduction is going to be prevailing for some more cycle, so what happens is, the next one, that is the second droop control strategy, comes into the picture, which is adopted in the DC-DC converter. So I battery references are being changed. So the master controller is now going to give a command for reducing the I battery reference. So these droop coefficients are named as R1 and R2, where R1 is nothing but delta I battery over delta VDC1, and R2 is delta V battery 2 over delta VDC2. So the current references of the various charging ports are coordinatedly regulated by IV droop. So there will be various ranges of vehicles which would be connected to the common DC bus, starting from a two-wheeler to a truck or a very big vehicle. So the current drawn by each and every vehicle, that is the reference current setting, battery current reference setting would be different for various vehicles. So similarly, proportional to the individual rating of the DC-DC converters, I battery reference also would be correspondingly reduced. Further dip in the DC voltage is reduced. So actually now we are on the verge of moving from the grid to vehicle mode to the vehicle to grid mode. But even before we can do that manner by means of slow charge, and subsequently then the operation changes over from the grid to vehicle mode. From grid to vehicle mode, it moves to vehicle to grid. Okay. So all these are being done by the coordinated control of sense by means of the gain parameters of the controllers are being tuned in order to enhance the stability of the system. And other than that, this Droop control is an outermost slow control. Okay, when compared to the fast inner controllers, the outer controllers. So subsequently, the outer controllers are a bit slower when compared to the inner controllers. And the outermost layer, we have the Droop control. So this action is even more slow. So with respect, when you compare the time constants of all the loops, so the outermost control now comes to the Droop control. And this Droop coefficients are also governed by the master controller. So this is a typical structure of the battery charging ports. So here we have the IV Droop constant R, and this gives a modulating signal, that is delta I battery reference. So therefore, the actual battery current references are now modulated. So the battery current references could also be made negative. Thereby, the mode of operation changes from G to V to V to G also. So now the duty ratios of all the converters are being changed. Subsequently, equation for the Droop control is given by this equation. So I battery reference nu is nothing but I battery Droop times delta V. So now the concept is the battery current references are being modulated with respect to the DC bus voltage. So now we are showing the simulation results. So once we are first of all
I think we again experienced some network issues. Hopefully the presenter will be back online soon. Yes. Okay.
hello.
Yes, we can hear you. Can you share your screen again?
Yeah, from which slide?
It was the slide with the control system of the Droop controller.
Do I have to share my screen again?
Yes, you have to share the screen.
Okay, I will share my entire screen.
Okay, we can share the screen.
Slides
okay,
are moving.
Simulation results. Yes. Yeah, we were
Are you
at the simulation results. Yes, we were at the simulation results at the beginning of the simulation results. You started talking about it. Yes, so we were here and then.
You want to continue with simulation results?
Yes, I think we were at slide 12.
The results.
Before the disconnection, I think we were at slide 12, so you can start with discussing simulation results.
From this slide number 14.
Before that, we were at slide number 12, I think.
12. Okay, I'll continue from the start from this slide. So
All
here,
right.
Slide number 12. Am I audible? Shall I continue with slide number 12?
Yes, we can. I think we covered this slide already, so we could start from number 12.
So proportional to the DC bus voltage, the I battery references are being modulated. So if the DC bus voltage reduces, correspondingly the battery current references are also reduced, and vice versa. So in that case, this Droop coefficients are being set in proportion to the individual rating of the DC-DC converters which are connected to the common DC bus. So this is the Droop control structure of battery charging ports. So here we have the mathematical equation for the Droop controller. Given like the new reference is nothing but the old reference plus the Droop times the dip in the DC bus voltage. So next I'm showing the simulation results. So here the frequency dip is being created by means of huge load addition. So initially the VSC inverters only participated in the frequency support, and subsequently the following a DC bus voltage drop, the current references of the DC converter, it will change the direction also. Battery current direction also could be changed. So here, first plot shows the grid frequency disturbance. The disturbance is given at t is equal to 0.1 seconds without any controller action. So we can see that the grid frequency dips from 50 Hertz to 40, and with the VF Droop, that is only inverter is now participating in the grid frequency regulation. In that case, the frequency becomes 49.998 something. So now, though it is giving the support, here it is giving the support, we can see that still there is a voltage drip which is prevailing in the system. And corresponding to this frequency support, we can see that the DC bus voltage also drops from 600 kV to nearly 500 kV. So DC bus voltage drops down, and the real power which is drawn by the VSC is being actually reduced, and that causes a dip in the DC bus voltage. So earlier it was drawing 500 MVA, and now that is reduced. So now the power which is being drawn is 410 MVA or 20 MVA. So now this is a simulation result for double Droop control. In the sense, following VF Droop, IV Droop also comes into the picture. So when IV Droop also is being incorporated into the system, along with VF Droop, now the voltage oscillations are even more smaller, and when the load addition is being removed, so load addition is followed by load rejection, and the frequency becomes stable. Again, it comes to 50 Hertz in a very short duration of time when compared to the conventional one, that is nothing but VF Droop. So following VF Droop, IV Droop also plays a very vital role in stabilizing the frequency. So the grid frequency support, which is given by the coordinated master controller, which incorporates both VF Droop and IV Droop, is superior when compared to the conventional Droop control strategies, which are reported in various literatures. So here, this is a simulation result for double Droop control, VF Droop control. So here we can see that at steady state, the converter 1 is drawing 100 megawatt. And whenever there is a dip in the frequency, the power drawn goes to even -2, near equal to -200 megawatt. So it is pumping power back to the grid. And following the removal of the disturbance, again it comes to nearly 100 MVA. So a zoomed version of that plot is shown in the below one. And the P drawn by the VSC2, that is second VSC, which is rated higher than the first one. First one is 100 MVA, the second one is 500 MVA. So here, actually, the Droop need not be actually proportional to the individual converter's rating. So it could be fixed by the master controller. We can fix the Droop accordingly. So here, instead of drawing 500 MVA, now it is drawing only 400 MVA. And this will manifest as dip in the DC bus voltage. And this dip in the DC bus voltage further causes dip in the I battery references. And the battery current references are being reduced. So in the sense, when the battery current references are reduced, the charging becomes lower and the oscillations in the DC bus voltage is also subsequently reduced. And the free support which could be given by the converter also increases. And that is why we are able to track 50 Hertz immediately after removal of this load. So these are the simulation results whichever we are showing. So the I battery references are being changed, and that subsequently causes the battery currents to reduce like this. So now we can see that converter 1, the current actually changes from 10 amperes to nearly 5.5 amperes. But whereas in converter 2, it changes from 10 to minus 10. Okay, so the amount of support which has to be given by individual battery charging systems can be controlled by means of incorporating this Droop. So though Droop is a slower one when compared to the converter controller speed, anyhow it gives a very important support to the grid. So it mitigates the grid frequency oscillations. So these are the conclusions. So either it could be in proportion, that is the Droops could be made in proportion to the individual converter ratings, or the operator can fix the Droop depending upon the priority of the electric vehicles which are connected to the grid, according to the driver preferences also. So under large disturbances, the frequency support provided by the VSC alone is not sufficient. So the battery charging units also have to be coordinatedly participating in the grid frequency regulation. So as the voltage drops, DC bus voltage drops, the current references of the battery are modified, they are being modulated. So in order to enhance the stability of the charging system, so VSC are made to participate in the primary level, and the converters are being made to participate in the subsequent manner. So the time constants of all the controllers are tuned to respond to the frequency error. So